Okay. I have a giant chat window obscuring everything, but yes, you can see that. Okay, awesome. And there are people here, and it's 1:30. And Bennett's bogarting the chat, talk about lab stuff. Okay. Um, so today, where I want to go with this is I want to spend a class talking about these four mechanisms. And so, next class, we're going to quickly revisit some oxidation chemistry, now in terms of PCC, PDC, and Jones oxidations, in terms of thinking about them as E2 eliminations. And then we're going to move on to some free radical chemistry for two lectures, and then we finish off with combining stuff back in and doing some more problems. But I really, really want to think about the competition between these four reactions. If you haven't already, I really recommend that you read. I think this is the first time I'm giving a specific reading that I'm recommending. I strongly recommend you read section 12.5 in the textbook and 12.6. This is on differentiating between elimination reactions and nucleophilic substitutions. And I find it, borderline offensive actually, that they have, I think, a total of 4 pages discussing this. Because this is really, really, really critical. And I think this is the subtleties, and this is where things matter. And maybe that's why they don't spend a lot of time talking about, because it's hard. Yeah, it's not even a page for each reaction. But we're going to just walk through a bunch of these things. We're going to talk about why we're thinking about the way we're thinking about these things, because there's a lot of complexity in these mechanisms. So again, last class, I finished off by talking about the fact that what we have here is we have four reactions always in competition with each other. That's what we've got. All four of them are constantly fighting out under any circumstance to occur. And all of them occur. Lara just asked if the SciComm can be done as group work. Yes, but if it's more than one person, you do need to approve it with me, because it can't be 5 people doing a work that one person is doing for another thing. Just some projects are too big for one person and they're really interesting, and that's fine. So I've approved a few group work projects already. Um, but if you have a new one, you haven't talked to me about it, and I haven't pre-approved it, come to me with that, and I'm fine with doing group work projects. That's cool. You can actually do some really cool things that way. But what we want to do is we want to figure a way to sort of bias these conditions so that only one of them occurs, the one we want, whatever the one that happens to be. So, this, I like to think all my slides are important, but this might be one of the more important slides for the course. So, what we're trying to do is predict which one of these happens. And rather than predicting the positive and really sort of predicting which one of these happens, what we're going to do is basically try and rule stuff out. We're going to try and find reasons why some of them are going to be slow. Because again, all four of these reactions are happening at the same time. What we want is 3 of them to be slow, 1 of them to be fast. And so we want to figure out reasons how we can slow down some of them relative to the others. And fast and slow is completely a relative term. It's just which one is faster than the other ones under these sets of conditions. At exactly that same speed, it might be slower than the other ones under different conditions, even though its speed's still the same. Like, a horse is really fast compared to a person, but really slow compared to a Lamborghini, assuming you can find parts for your Lamborghini. So, what we're doing here is we're trying to basically figure out what's fast, what's slow. I'm going to get to primary halides. So strength of base or nucleophile determines order of reaction. So what do I mean by that? Strong negative charges don't want to be negative. That's pretty clear. What does that mean for us? That means that they're often involved in a rate determining step. So strong bases, strong nucleophiles, could be the same thing, just we're calling it something different because it's doing something different, tend to do SN2 and E2. And that's because the nucleophile or base is involved in a rate determining step. And because it's reactive, it's not going to wait around for the leaving group to wander off, which is what it needs to do for the SN1 and E1. It's going to get involved. So primary halides, usually SN2, occasionally E2. So again, what is a primary halide? Well, a primary alcohol is an OH attached to a primary carbon. A primary halide is a halogen attached to a primary carbon. So halogens, again, are bromine, iodine, chlorine. And so a primary halogen would be something like that. This would be a secondary halogen. And this would be a tertiary halogen. So it follows the same nomenclature that we've been using. We're talking about halogens, halides, it's like oxide, nitride, we never say carbide, but halide is that ending that basically says it's attached to something else. Whereas a halogen is the name for the entire atom. Tertiary halides go E2 under strong base. Please see point number 1. So if you have a strong base, it's strongly reactive. It favors SN2E2. The SN2 is impossible for a tertiary halide. We discussed that because you need that backside attack, and the backside is too crowded for a tertiary halide. If you have a weak base, you're going to make a tertiary carbocation, which is awesome. That doesn't help you determine between SN1 and E1 because they both make tertiary carbocations. And it's the same tertiary carbocation. But a tertiary halide will not go SN2. Point 4, reactions of secondary halides are difficult to predict because they could do any of these. And so we have to really look at all the other finer things. And point 5, some nucleophiles favor substitution or elimination. We're going to discuss sort of a small list of those once we get to that a little bit later in today's lecture. What we're often going to be doing, and I think one of the things to constantly think about, is we have kinetics, we have thermodynamics playing into this. And what we need to think about with that is, well, you can think about this any way you want. I'm not going to tell you how to think. But let's think about our cat with our door. We had our video. So, just because it's Monday, let's watch this video again. You know what? We can probably find another cat with video. It is the #1 search on my YouTube, which tells you how much YouTube I watch. So let's find another cat video.
March, I'm home.
Okay. Well, that's funny, but I'm going to see if this works. Oh, God, there's a ton of cats coming through this door. Okay, this will work. I'm just going to stop sharing for a second. And I'm going to share from this screen. Screen 1.
March, I'm home.
Mom, Dad, I'm home.
So what we have here is cats coming through a cat door, and you can see it can be kind of difficult.
March,
And so
I thought we agreed you'd cut back on the kitty treats.
I'm going to mute this because the sound is stupid. So, but kitty treats are important because what we have here is kinetics and thermodynamics. And the thermodynamics is how much does that cat want to get through the door? If the cat really wants to get through the door, this is a downhill process. That cat is eventually going to get through the door. Kinetics is how long does it take the cat to get through the door. And so this cat is getting increasingly big. And you can see that this is kind of like a very challenging nucleophilic displacement. That cat really had to hit the angle right to get in through that door. So thermodynamics is how much does the cat want to go through the door. Kinetics is how fast does the cat go through the door. And now there's a bunch of, okay, well, let's watch something with raccoons. There's a lot of raccoons. I have no idea what's going to happen. But We'll let the raccoons. Oh, he's gonna feed the raccoons. That's not a good idea, man. Okay. You know what? This is just not going to be helpful. I'm going to stop sharing. You can look up videos of raccoons if you want in your own time. God, this is long. It's like 5 minutes of a guy feeding raccoons. The world is a weird place. Sorry, for some reason I have windows open everywhere. What the hell? Um, escape. Sorry, I'm obviously having technical difficulties. What is this thing? I've turned on something that I can't stop. It's got a mind of its own now. There. Rescuing myself from my own incompetence. So, kinetics is about how easy it is to get through the door. And kinetics in these reactions depends on both the size of the cat and the size of the door. If the cat's smaller, the nucleophile is smaller, it's easier to get through the door. If the cat's bigger, it's harder for the cat to get through the door. That's kinetics. Thermodynamics is how much the cat wants to get through the door. And so, you can have a cat who can easily fit through the door who doesn't really want to go through the door, and then you get no reaction. You get no cat passing through the door. Whereas you can get a really big cat with a really small door and it really, really wants to get through that door, and eventually, as we just saw, it will. Um, that might be okay. There's really good comments in the chat thread. I'm not going to comment on the use of Reddit subreddits. I really hope that's one about fat cats. If it's not, I'm concerned. Then good. That's useful. Yeah, I think what we're about to see is what happens when one atom of sulfuric acid catalyzes a reaction with an awful lot of raccoons. And I think you're right, Mohammed. I think that is what was going to happen. And raccoons are awful. I agree. Um, okay, I think I'm caught up on a chat window. So, with this door cat dichotomy issue philosophical question really comes into point number 4, where the secondary halides, it really does depend on both the size. That it is a secondary halide tells us how big the door is. Depending what the nucleophile is or the base is, tells us how big the cat is. And so we can get either SN2s, E2s, SN1s, or E1s on secondary halides depending on the relative desire of the cat to get through the door and relative size of the cat. Okay, we have a definite disagreement about raccoons going on. Okay, so let's give the substitution and elimination products you would expect from the following reaction. 1 iodo, 1 methyl cyclopentane. So everyone draw that at home. This is me trying this is like my one time a year when I'm kind of giving into flip classes. So we're just going to do some work problems. Wouldn't secondary halides favor elimination since sterics don't matter with them? Sterics still can matter with eliminations, and they don't necessarily because they're not so hindered that the substitutions can't occur. They're really on the fence. Yeah, there's really good video of raccoons trying to wash cotton candy. It's sad. I feel for the raccoon. Okay. I think there's some courses over in biology where they talk about raccoons. I have no idea what they do over there. Maybe it's urban biology or something, which is probably a lot less exciting than it sounds. Okay. So I know the vast majority of the people in this class are biologists, though maybe not who are here right now. And that's awesome. So I started too. Before I saw the light. Okay. So what we have here is 1-iota, 1-methylcyclopentane heated in ethanol. There's heat. So there's a bunch of things going on here. We're already getting some information. There's a lot of energy in this system. What we should be doing when you're doing this is you should be now looking at this and going, okay, lots of E. So what does this help? Well, it actually helps SN1E1 because high energy intermediate. So if we go back to the SN1E1, they're going through a carbocation intermediate. Carbocations are not stable. So the more energy you've got in the system, the less you care that this is not stable. If you're doing something really, really, really cold, you don't make unstable things. You're moving really slowly when it's really cold. You're not going to go up a high energy hill to make some sort of crazy ass carbocation when you can just kind of slowly slop your way through an SN2 or an E2 reaction. It doesn't need to go through that high energy intermediate. So there's heat. You should be thinking, okay, carbocation is possible. Not saying it's likely, but it's possible. What we're thinking on this guy is not strong. It's a neutral molecule. I think when we talked about substitutions, we had a list of strong and weak nucleophiles. And this one is on the not strong category because it is a neutral oxygen species. What I am going to note is I like dividing my molecules into sticks and balls. And what I mean by that is, does it look like a stick or does it look like a ball? And this one looks like a stick. So sticks plus atoms are not balls. Atoms are also not balls, they're also like sticks. So sticks are things that are stick-like. You can draw them. You can sort of imagine yourself poking yourself with a stick. So we had some azide. These are all sticks. They're very straight. They have small a values. So if you're trying to navigate into that antibonding orbital and you're trying to, bypass all the steric bulk of stuff that's blocking you from getting to that antibonding orbital, you want to look like a stick. Or you want to be an atom. Atoms are great too because atoms are like they're really small. Then you got balls. Balls are things that don't look like sticks. So, isopropoxide, you've got ball-like character there because now suddenly you're branched, so you're bigger. Or, some sort of disubstituted amine. So you're moving towards ball-like. Then we've got kind of the extreme ball. And these are so ball-like that I guess you could call them super balls. I have way too much fun. So they're just very big balls. And what that means is they're really shitty nucleophiles because they can't navigate their way to that antibond orbital because they're just so big. These are huge cats. These are cats that will never get through a door. The ball ones are kind of the cats that we've seen in these videos where the cat is struggling to get through the door, whereas the sticks and atoms are nice skinny cats like my cats, which have no trouble getting through like cracks in a freaking wall or something. Because they're narrower than their whiskers and they're tiny little guys. Actually, they've shown up on these videos. They're really small cats, like micro cats. They are liquid. I've also I've moved in sort of nanoscience lately in my science, and so I've gone from big bulky cats that I used to have to these little micro nano cats. Right. So, not strong. That's our nucleophile. It's also our solvent because there's nothing else here. And it's a protic solvent. And it's our solvent because there is no other solvent. It's the major component of the mixture. So we got a protic solvent, we got a not strong nucleophile, we got lots of energy. We have a tertiary leaving group, tertiary halide. We're going to abbreviate leaving group as LG. I think I've already done that. And we have a really great leaving group. This isn't like some sort of silly ass chlorine leaving group. This is iodine. This is the queen of leaving groups. Okay. Great leaving group, tertiary leaving group, not strong nucleophile, protic solvent, lots of energy, and it's kind of a stick. This is kind of the full court analysis that you need to be kind of making on these things. Thinking about all these different components. Then what we do, you don't have to do this. I'm going to do it right now. So I'm going to kind of write all these ones in. So we're going to look at these 4 different reactions, and we're going to cross shit out if we can. So I'm going to look at this and go, I do not have strong basic conditions. I just talked about sticks. There's a whole thing up there in the top right-hand corner about sticks. The nucleophile is a stick. It's straight, it's sticky. This is not strongly basic. The nucleophile doesn't have a great desire to react. It's ethanol. It can sit there in a bottle for a very long time and increase in value. And so it's not in any hurry. SN2 and E2 normally require a strong base or a strong nucleophile. We don't have that. I'm going to cross those out. And it's not because they're not going to happen. It's going to be because there's no particular reason for them to be favored. They're not as strong. Now, SN1 and E1, I'm looking at my leaving group. I've got a tertiary leaving group. That's good. I like that. That's favoring both of them. I can get carbocations. I've got heat. That's good. That favors carbocations. I've got a protic solvent. That's good. That favors carbocations. I've got a really good leaving group. And if in the rate determining step of the SN1 and E1, the only thing that happens is the leaving group leaves. And the better the leaving group, the easier that is. So that's good. It's favoring carbocations. Everything here is favoring carbocations. I like both of these. Now, what I'm trying to do is, okay, so which one of these do I prefer? And this is where we kind of come down to, okay, everything is kind of tied up. I'm going to make the intermediate, which is this carbocation we've been talking about so much. And now it's going to react with our nucleophile or base. And it can do either. I am out of space here, and I think I have another example in the next question. I do. I'm going to quickly escape out of this, and I'm going to insert an extra slide. Wish there was a way to insert a slide when you're in the middle of a talk. It probably is. I will end up clicking the wrong button, and bad things will happen. So we have our carbocation. We've got three, technically four, but three effectively different things that can happen. The first one is a substitution. Alcohol go carbon. Ugh. Molecule of ethanol comes in and takes away that pesky little hydrogen. So we get a substitution. This went by the SN1 mechanism. The second thing that can happen is an elimination. And this is, if you remember, I really despise using name reactions and things for stuff, but I'm going to stick with it because it's easier. I'm going to talk about the Zaitsev and the Hoffman eliminations, and then the Markovnikov and anti-Markovnikov. That's going to be the stuff I'm really going to stick with names in this course. Other than that, I'll try to avoid them. But this is going to be the Zaitsev style, and we can also get a Hoffman elimination, where we attack the most accessible proton, not the most stable. Okay, so we got a Hoffman, we got a Zaitsev, and we got an SN1. Relatively simple, and it's upside down. For me, probably right side up for you. Relatively simple, except it really, really isn't. And now we're trying to think about which one of these is more likely. So the question I think asked, give the substitution elimination product you expect from the following reaction. Drawing all three of those would be acceptable. But they're not equally likely. If I asked you which is the major one from these, then what you end up doing is you have the same carbocation in all these cases, so now it comes down to the nucleophile. And in this case, our nucleophile is a stick. And sticks make it more of a nucleophile. So we are going to favor the SN1 in this case. Okay, so of options 2 and 3, which one do you think is more favored of 2 and 3, of the two eliminations? Do we prefer 2 or do we prefer 3? Okay, a lot of 2s coming in, including some new names who haven't actually done this before, so welcome to using the chat window. Yeah, it's 2. Almost all of you are right. And again, it's because it's the more stable double bond we are generating, and it's more stable because it's more substituted. We've got 3 carbons attached to the 2 carbons on a double bond. What I mean by that is there's the 2 carbons, carbon 1, carbon 2, carbon 3, whereas for these 2 carbons, there's only 2. So the top one is the more stable double bond. The starting materials are the same, the products are different. The one that's more stable is going to have a more stable transition state leading to it. And so you're going to get a more stable product there. So this is less stable. So this is the second favor, less favored. Okay, 2 really good questions in a chat. So why is ethanol a weak nucleophile? it's a weak nucleophile because it's not charged. It's not so much that it's a weak nucleophile, it's not a strong nucleophile. So it doesn't have any great desire to react because when ethanol reacts, it becomes charged, and this is a worse outcome for the ethanol component of it than when it started. So we've gone up in energy as far as the ethanol is concerned. So it's not particularly eager to do that, and so it's a weak nucleophile. And Keith asked, why is SN1 favored over E1? They're pretty close. I'm going to say the SN1 is favored because our nucleophile is shaped like a stick. It's more easy for it to get to that backside attack or approaching the carbon, which is more crowded, than it is stripping a hydrogen off the surface. Like, think of it with, if we go back to our cat and door analogy, the SN1, like the substitution, requires the cat to go through the door. The eliminations require the cat to bounce off the wall and chip it, because they're taking one of the protons that are off the surface of the molecule. They're a lot more accessible. And if your cats are anything like my cats, they bounce off walls a lot, especially if they're chasing toy mice. And so the chances are the cat is much more likely to randomly bounce off a wall and take away a hydrogen that's on the surface of the molecule than it is for it to go through the door. Now, the smaller the cat, the more likely it is to go through the door. And so stick-like cats can go through the door, whereas ball-like cats tend to do eliminations and tend to take off a proton just on the surface. Yeah, exactly. So if we had a different nucleophile, the E1 would be favored. So if I did this exact same question here, but I changed the nucleophile to a ball, E1 Zaitsev is favored. Now, I can even do something more. If I change the nucleophile to a superball, the E1 Hoffman is favored. Because the Hoffman requires, like, if you're thinking, okay, one ball, there's still some steric bulk around this hydrogen because it's attached to multiple carbons. Whereas this carbon is stuck out in the middle of nowhere. And so if you take a look at the space filling models, I know you've done this in Spartan, the hydrogens at the end of a chain actually look kind of accessible. The ones in the middle of the chain, like, they're all kind of crumped up and crumpled and they're hard to get to. So the superballs are huge. They aren't going to go near stuff that's in the middle of something. It's hard to get to. They're going to take the easiest to get hydrogen. The easiest to get hydrogen gives you that Hoffman elimination. And so just by even starting with exactly the same carbocation and just adding extra carbons to the ethanol, to go from ethanol to isopropanol to terbutanol, all we're doing is increasing the steric bulk. All we're doing is making our cat fatter. And that changes us from favoring the SN1 to favoring the E1 where we make the more stable double bond, to favoring the E1 where we make the less stable double bond, but we go through interaction where you're getting a more accessible hydrogen. Yes. So, Nulia, you're absolutely right. So because the angle ball-like are challenging to get in there at those tight angles. Janik, yes, you're right. You're going to prefer 2 over 3 normally because you're going to get a more substitute double bond, which is more stable. And so the transition state leading to that is going to be more stable. And so it's easier to make. Now, the Hoffman reaction gets you less substitute double bond because it's easier. And so Carly came in with KOT, butyl B, Zaitsev, or Hoffman. It would be Hoffman because it's huge, superball, but it's a very strong O minus. And so you're not going to do an E1 or SN1, you're going to do an E2. So let's do a few more examples. So here, 3-bromo, 3-methyl pentane. Take a second to draw it out. Hopefully you drew that. If you didn't, please go back to naming. We have sodium methoxide. Uh-oh. I'm worried this thing is starting to overheat again. We don't have with that last time. I'm going to sit it up on top of it and hope for the best. Again, this is stick-like. Oh, shit. So I'm expecting it to do... Yeah, thanks, Victoria. I'm expecting it to do an SN, like nucleophilic reactions. It's a strong base, strong nucleophile. We're going to favor E2, Sn2. It's not getting a lot worse. I sat this thing up. There's good airflow in my office. Lots of air exchanges to help us prevent COVID. So E2, Sn2, that's what because it's strong negative. It's not stick-like, so it's E2, Sn2. This is because it's big negative. I'm really sorry for this. But we've got a tertiary leaving group. And now we know that SN2 do not work on tertiary leaving groups. So if we're looking at our 4 reactions, we have a strongly negative system. It's not going to wait around to form a carbocation. That takes time. The leaving group's got to leave. It doesn't want to leave. It doesn't want to make a big positive carbocation. It's like me at 6 in the morning or 4 in the morning or whenever I get up. So E1, SN1 are ruled out because you're not going to make a carbocation because you're not going to wait to make a carbocation. Under strong basic conditions, you're going to do something fast. The SN2 is ruled out because it's a tertiary leaving group. That leaves you only with the E2. It's helpful that in his question he said predict the elimination product, but I could have said predict the product because the E2 is the only thing that's feasible under these conditions. Now you can get 2 different E2s. You can get the Hoffman E2 or the Zaitsev E2. And so for that, you need to think, is my base a ball or a super ball or a stick? Now, if this was an accessible leaving group, we have a stick, we would expect an SN2 reaction. But it's not an accessible leaving group, it's a tertiary leaving group. So even, whether it's a stick or not doesn't matter, it's not going to help us with the SN2. But a stick makes for a good Zaitsev elimination. There's no reason for it to do the Hoffman. There's no reason for it to take away the most accessible hydrogen when it can make the most stable double bond. So we're going to do the Zaitsev elimination. And we're going to get the double bond in the main chain. Now, we still haven't covered all of it because I haven't drawn you anything that's possible. There's another Zaitsev that's possible. And I don't mean eliminating the other side of the double bond. That doesn't matter. But I have these 2 different E and Z possibilities. Now, to figure out which one I'm more likely to get, I have to go by, is there anything restricting? We didn't draw this in explicitly, so I'll do it explicitly now. But remember, you need to be anti-periplanar between the leaving group and the hydrogen you're eliminating the E2. They need to be across from each other. Now we've got 2 hydrogens I can eliminate from that carbon. From the way I've drawn it here, with this rotation, I have to eliminate this hydrogen to get this product because they're across. Alternatively, I can rotate around that bond and I can eliminate the other hydrogen, I'll get the other product. There's nothing stopping me doing that rotation. So I can get either one. So then the question is, which one is more stable? Trans is more stable. Which one's trans? They're both kind of trans. You can't use trans. So we're going to do E versus Z. And E's are almost always more stable because they're less sterically hindered. Think of it this way. What's bigger? Size-wise. Weight-wise, too, you always want to think about weight for EZ, but size-wise, you've got a methyl group here and you've got an ethyl group. Ethyl is bigger than methyl. So I want my methyl away from my ethyl. There's steric hindrance here. These are two things that are banging into each other. That's what those brackets facing each other mean. Whereas here it's just two methyls, which is better than a methyl and an ethyl. Now, admittedly, this is not great selectivity. I'm going to get a kind of a hopeless mess of stuff. But I am going to get mostly the one on the left. Okay. 211. 1-bromohexane. One, two, three, four, five. It doesn't really matter how many carbons there are. 6. In sodium methoxide and ethanol. We're going to move through the oxidations and eliminations fast next class. We're going to do a few more examples. Okay. Now, the solvent here is a protic solvent. That's got you thinking, oh, protic solvent, I know that one. It's SN1 and E1, protic solvent. Don't get too excited about the protic solvent. Yeah, it's true, all else being equal, that's true. That's not as important as almost anything else going on here. We've got a strong base, we've got F oxide, we've got O minus. Got a good leaving group. I've got a primary leaving group. So your Spidey sense should be going off. My thingy is like a stick. Ethoxide is a stick. That says stick. I promise. So I got a stick. It's a strong nucleophile because it's O minus, so we're not going to wait around for the carbocation to form. And even if we did wait around for a carbocation to form, it will be a shitty primary carbocation that's never going to form. So we're down to E2 versus SN2. It's primary, so our door is huge and our cat is small because our cat is ethoxide. Big door, small cat, I'm looking at an SN2 reaction. It's O minus because it's sodium ethoxide, and sodium salts dissociate completely. Yeah. When you draw a nucleophile, it looks more like a stick than a ball. You can use other things if you like. Pens instead of sticks. I don't know. You could ignore all these things altogether. That's fine too. It's just this model actually does work. It explains reality, which is kind of nice. I'm really sorry. These are not meant to be dotted lines. 1, 2, 3, 4, 5, 6. What if I draw real slow? There we go. What made it SN2 over E2 is we got a stick. SN2s tend to be more thermodynamically favorable. The reason they don't always occur is because they can be slower because the site can be crowded. But whenever possible, you want to do the substitution. It's just sometimes you're too crowded to do the substitution. But in this case, we're about as uncrowded as we can get. Yeah, that's what I want to start talking about next class. I think I'm going to leave it be though for now. What I'd strongly recommend, you'll get the most out of next class, is if you take a look at some of the examples and the assignments, you take a look at some of these practice problems and try them out. Because we're going to try and kind of expand on this and sort of show how this can get a bit more complex. Uncrowded because it's primary. Yes, both of them are uncrowded. Both it's primary, so you can again you're thinking about size complementarity here. It's primary, so that means it's a big door, and it's a stick-like nucleophile, so that means it's a small cat, and that's the combination you want for SN2. It's easy to get at. Yeah, and I thought it was just there because the charge thing takes precedence. Worry about things that are charged. Right, this whole course has been about worry about the charges. Neutral things, you worry about them when you've dealt with all the charged things, and you can't find anything to use them for. Otherwise, charged things take precedence. The reason why the ethanol is there is the way we make sodium methoxide. You literally take a bucket of ethanol and you drop in chunks of sodium, and the sodium reacts to generate hydrogen gas and sodium methoxide. E and Z. Yeah, well, it's E because the two big groups, the methyl and the ethyl group, are on opposite sides of the double bond. And Z because the big groups, the methyl compared to a hydrogen is big, and the ethyl compared to a methyl is big, are on the same side. So stick and ball. So let's just think about, I'll draw them on here. Which H gives E and Z? Well, if I drew this stereochemistry the way I've done it here, this back H is going to allow this thing to eliminate in this exact same form I've drawn it here, which will give me the E. And I'll have to rotate the double bond, I'll have to rotate this carbon bond, or this bond here, to put the methyl group up. And when I do that, this hydrogen here will be at the back, and this one will be at the front, and I will eliminate this hydrogen with the bromine to get the Z. Okay. So sticks and balls. So what we want to think about, let's just think about a secondary halide. No, you know what? Let's take it to an extreme. Let's do a tertiary halide. No, because they're not very reactive. Okay, let's think about a secondary halide. Here we go. So there's a hydrogen going back out of the plane, carbon coming towards us. Yeah, I know it's the monitor's overheating, and so it doesn't work anymore because I think that the sensors start failing. Let's think about what that actually looks like, though. I've just drawn it that way, and that's how we think about it, but that's not what it looks like. What it looks like is, okay, what I'm interested in is this anti-bonding orbital between the carbon and the bromine, because that's what I want to hit with my nucleophile. And then this carbon has got stuff over here, which is this methyl group, and it's got stuff over here, which is this methyl group, all blocking it. And so I need to hit this target here. Now, if my molecule is small, like iodide, or is a stick, like a thoxide, think about the surface of that. I'm going to say it looks like a banana. Then hitting this target is feasible. Whereas if my molecule is a ball, like isopropoxide, like that's what this surface of this molecule looks like. It's big and round. It's a lot harder for this ball to access here because he needs to be a bit pointy because There's stuff sticking out on either end here because of these methyl groups, like they're blocking space. They're making it difficult to approach this anti-bonding orbital for this carbon-bromine bond. It's kind of like I've got these things running interference. And when I'm big like a ball, and this actually looks like a little man, right? The isopropoxide looks like, an armless man. He's not very effective at attacking that spot because he's kind of ball-like and he kind of bounces off these big bouncy surfaces, whereas a stick can stick it up right in there and get into that corner because it's smaller, so it can do its stick thing. Okay,